This is a continuation of EE5508 lecture 3. In the previous session, I think we stopped here at table 3.1.1, compositional dependence of band gap energy in ternary 3-5 semiconductors at room temperature. So basically, this is a table show a series of 3-5 semiconductor alloy and the direct energy gap or the band gap. Again, the notation, the band gap measure from the top of valence band to the bottom of the conduction band, both at the gamma value. The indirect energy gap is also the same, measure from the top of valence band to the bottom of conduction band at the X value, and the energy gap measure from the top of valence band to the bottom of conduction band at the L value. I would like to make a correction in the previous slides, show the band gap of the aluminum gallium indium phosphide. So basically, aluminum indium gallium phosphide, okay, makeup of aluminum phosphide, gallium phosphide, indium phosphide, okay, and that form the aluminum gallium indium phosphide quaternary alloy semiconductors. So if I were to take this shape, okay, and impose on the previous slides that we discussed about the band gap as a function of lattice constant, the aluminum phosphide will be somewhere, okay, above the gallium phosphide. Aluminum phosphide is an indirect band gap material. So if you take this shape and superimpose onto here, you expect, okay, aluminum phosphide, gallium phosphide, indium phosphide, okay, to form the quaternary alloy semiconductors. So aluminum phosphide lattice constant is somewhere around here. Okay. So gallium arsenide, okay, again is somewhere, okay, below, okay, this shaded region. Of course, you can grow aluminum gallium indium phosphide on gallium arsenide lattice constant. So within this region, okay, this vertical region, within the yellow shaded region, you can grow on gallium arsenide substrate for aluminum gallium indium phosphide quaternary alloy semiconductors. Okay, this is basically just to recap that instead of plotting band gap as a function of lattice constant, sometimes you can also plot, okay, a contour plot of the band gap, okay, as a function of composition. Of course, you need to measure sufficient the band gap energy in order, okay, to have this kind of a contour plot. And again, in this graph, the red line is basically anything that falls on this red line can be grown on indium phosphide substrate. Okay, so if you want to grow on indium phosphide substrate with a band gap of 0.789 eV, this will be the intercept. Okay, and that gives you the composition of 0.4 and a composition of about 0.9, okay, for the Y composition. Okay. Similarly for this graph, okay, you can grow on gallium arsenide substrate, and let's say you want to grow a quaternary alloy of gallium indium nitride arsenide or gallium arsenide substrate with a band gap of 1 eV, okay, then you would have a composition of X 0.028 and Y 0.08. So the example 5, I will leave it to you for your own exercise. Next, 3.1.6 is we will discuss spinodal decomposition. So basically, spinodal decomposition is a process where the alloy can separate into distinct phase. So it can separate into two phases, and the two phases can coexist. So let us look at this phase diagram. This is the temperature, okay, or you can take it as a growth temperature, and this is a solid phase composition. Again, the composition ranging from 0 to 1, okay. Basically, the diagram is symmetrical around the composition of 0.5, okay, which is the case for a regular solution model. Now, the blue dashed line, okay, is known as the binodal curve, okay. The red dashed line is known as the spinodal curve. The blue region inside here is known as the binodal phase, or the phase is basically metastable, okay, which we have discussed before on what is metastable stability. Now, the red region inside here is known as the spinodal phase, which means the phase is unstable, okay, and this is where the two phases can coexist, and sometimes we will call this the miscibility gap. So again, remember, miscibility is the property of substance that makes all proportion, okay, of the substances, and they can fully dissolve in each other at any concentration. So substances that do not mix are said to be immiscible. So, for example, water and oil. Now, the blue region is the binodal phase, and sometimes we call this phase is the metastable. When we say metastable, means it's kinetically stable, thermodynamically unstable. It's still a single phase, okay, of the substance. So basically, if you assume the atoms is down here, okay, energy as a function of spatial diagram, it's basically chemically stable. But if you subject the system to some heating, there's a possibility that you overcome this barrier and the atoms will come to this center point or the minimum point. And then basically this is thermodynamically stable, okay, occur for the atom to occur at this point. So at this point, it's kinetically stable, but thermodynamically unstable, because by subject the system to some heating, okay, the atoms can overcome the barrier and settle over at this global minimum point. So the system is stable to small fluctuation, okay, of the temperature, but it's unstable to large fluctuation. So for example, you grow the material in the metastable phase, okay, at certain temperature. After the growth, you subject it to some heating. It could become thermodynamically unstable, okay, and it will move from here to here. So down here is basically metastable phase. Now, phase separation occurs when the system is within this miscibility gap. And usually in the unstable region, the growth is by spinodal decomposition, meaning that it grows into two distinct phases. Down here, the system in the metastable region, the growth of the material is by nucleation process. So growth techniques such as molecular beam epitaxy, sputtering, metal organic vapor phase epitaxy deposition are typically far from equilibrium, which is the stable phase. And usually it's in the metastable phase for such deposition technique. But they will grow, of course, without decomposition. But as I said, sometimes after the growth process, you subject to the substance to some heat treatment, okay, it will become thermodynamically stable, but it can also lead to decomposition. Now, usually we'll try to grow the material at low temperature. Okay, again, high temperature grow, basically, you will lead to decomposition of your precursor of your growth deposition system. So all your growth deposition system, okay, are basically made up of either stainless steel or some alloy material. And the material cannot be subject to too high a temperature heating. So the deposition system itself, okay, even though it basically contains the material, okay, or you have cell that contain the material itself will have to subject to heating, okay, and at the same time, the whole deposition system also subject to heating. But remember, your deposition system itself is also built using materials. So usually we're trying to grow the materials, okay, at a lower temperature. And furthermore, your CMOS processing is around 400 degrees Celsius. So your end process of your growth, you do not want to grow at very high temperature. Now, this is an example of a spinodal decomposition in indium gallium nitride. So let's say I want to grow indium gallium nitride and gallium nitride, multiple quantum well. This shows a cross-sectional image of a transmission electron microscopy. So you grow indium gallium nitride, indium gallium nitride, indium gallium nitride, indium gallium nitride. So indium gallium nitride form the well, gallium nitride form the barrier. 4 period, that means you've grown in the single quantum well 4 times. So indium gallium nitride, and then indium gallium nitride. So indium gallium nitride form the barrier. The gallium nitride form the barrier. Indium gallium nitride, okay, form the well. So you have gallium nitride, indium gallium nitride, and gallium nitride. So this is one period, okay, of a single quantum well. And then you grow another period, and then another period, okay, of another single quantum well, and another period. So this is 4 period of quantum well. We call this a multiple quantum well. Now you can see that in the layer of indium gallium nitride, there are small dark spots. Okay. The reason is because the indium gallium nitride actually decomposes into a indium rich quantum dot. So these are indium-rich quantum dot embedded in the indium poor matrix, which means that indium gallium nitride, this layer, okay, let's say if I want to grow 30% of indium, 70% of gallium, but the dot itself actually separated into a distinct phase. It becomes indium 40% and then gallium 60%. Okay, these are the dots due to the indium gallium nitride. And the original layer, which we call the matrix itself, or the layer of the matrix itself, will have deficiency of indium. So those layers actually will have indium poor indium gallium nitride, or we call that the indium poor matrix. So therefore, this is known as the spinodal decomposition. The alloy decompose into an indium-rich quantum dot phases. Let us look at another example, figure 3.1.15. This is basically an indium gallium nitride relaxed material. That means it could grow on the sapphire, and the lattice mismatch is so large that it's like 30%, so that there's no the interface cannot accommodate the strain, so the indium gallium nitride is relaxed. So this is the growth temperature. This is the composition. X equals 0 is gallium. X equals to 1 is X equals 0 is gallium nitride. X equals to 1, okay, is indium nitride. Okay, based on this indium gallium nitride alloy. So similarly to this phase diagram, okay, this is the binodal curve, the black solid line. This is the spinodal curve. So inside here is the unstable phase, or the spinodal phase. Down here is the metastable phase, and down here is a stable phase. Let's say I want to grow indium gallium nitride at 700 degrees Celsius. And I grow the indium, okay, at 0.05, which is 5% of indium, the composition X. Or I want to grow at 20% of indium, or 0.2, still at 700 degrees Celsius. So within this range, okay, is the metastable phase. So if I grow at 700 degrees Celsius, and I want to grow in the metastable phase, I can only grow within the range of 0.05 to 0.2 of indium, okay, for indium gallium nitride. Anything beyond 0.2 at 700 degrees Celsius, I will go into the spinodal phase, which means that if I go indium gallium nitride in this phase, okay, I may not be able to get a homogeneous, perfect random alloy of indium gallium nitride. I may start to form some indium gallium nitride quantum dot with very rich indium, okay, embedded, okay, inside the alloy itself. Now, for this graph, okay, the indium gallium nitride is grown on gallium nitride and is straight. So basically, at the interface, the interface can accommodate the strain. when you grow indium gallium nitride on gallium nitride. Of course, up to a certain critical layer thickness. And the phase diagram you can see is very different from this one. It actually shifted towards the right. So right now, I can grow a higher composition, even at a lower temperature. So let's say I grow at 300 degrees Celsius instead of 700. Then I have this composition range, okay? Around more than 30% of indium, and all the way probably up to 55% of indium for indium gallium nitride at low temperature and in the metastable phase. So by straining the indium gallium nitride, or we grow strain indium gallium nitride on gallium nitride, I can change the phase diagram. I can actually achieve to grow at a higher composition, okay, for indium gallium nitride for my desired property. Next, section 3.2, heterojunction. In semiconductor heterostructure, if you have two different semiconductors are brought into contact, for example, you grow epitaxially on one semiconductor on top of the other, you'll form the heterostructure, or the junction, we call that the heterojunction. If you have similar material, you go gallium nitride on gallium nitride, maybe you grow a p-type gallium nitride on an n-type gallium nitride, then we call that the homo junction. So fabrication of heterostructure, okay, by epitaxial growth is the cleanest and most reproducible method available today. So the property of such heterostructure is important for many heterostructure devices, including a field effect transistor, bipolar transistor, light emitting diode, lasers. So here we show three types of, we call that the band alignment, when we bring two different semiconductors into contact. So in the energy diagram, if you grow, let's say, aluminum gallium arsenide on gallium arsenide, okay, Mother Nature itself basically will develop this into a type 1 band alignment, where the small band gap material, gallium arsenide, is sandwiched by a large band gap material. Sometimes we call this a type 1 band alignment, or we call this the shredded alignment. Another type of band alignment we call the type 2A band alignment, or the staggered alignment. So let's say I grow gallium arsenide antimonide on indium gallium arsenide antimonide. You can see that this is like a stack. So this is a staggered band alignment. And the other type is known as a type 2B, and this is known as the broken gap alignment. So if we try to grow gallium antimonide and indium arsenide, okay, the gap is broken. So this is the band gap of gallium antimonide, this is the band gap of indium arsenide. Okay, and this 0.15 EV is the broken gap. So for this course, we will focus on type 1 band alignment. And we will discuss this heterostructure in conjunction with type 1 quantum well, okay, which is basically based on type 1 band alignment. So type 1 band alignment, let's say I grow Aluminium gallium arsenide, 30% of aluminium, okay, the aluminium gallium arsenide. The band gap itself, okay, is 1.8 eV. The gallium arsenide is 1.4 eV. And for type 1 band alignment, the small band gap is sandwiched in between by a large band gap. So this is the interface, okay, and that forms the heterojunction. This is the conduction band offset. Okay, it's the difference between the conduction band of gallium arsenide and conduction band of aluminium gallium arsenide. Similarly, there is also a valence band offset. So delta EC plus delta EV is equals to the difference in band gap of aluminium gallium arsenide, okay, minus of the gallium arsenide band gap. So delta EC plus delta EV is equals to the difference in the band gap between aluminium gallium arsenide and gallium arsenide. Let us look at one example. The gamma XL conduction value of aluminium gallium arsenide can be expressed in the following equation. So this is goes like x squared dependent. So it's a quadratic equation. Again, the notation is the first symbol gamma refers to the top of the valence band. The second symbol refers to the bottom of conduction band and gamma, and x and L value. So plot, okay, this energy as a function of x in one graph. So you can plot the graph, okay, energy gap as a function of composition. X goes to 0, okay. If x goes 0, there's no aluminium, so it's gallium nitride. X goes to 1, is at the other end is 1. X goes to 1 is aluminium nitride. So this is the graph quadratic equation for E gamma gamma. This is the open circle is E gamma X, okay, and this is E gamma L. So at x goes 0, you can see at this point is the band gap of gallium nitride of 3.38 eV. At x goes to 1, this is the band gap of aluminum nitride, which is 5.1 eV. So you can see from the graph, okay, E gamma gamma is the lowest energy up to x goes to 0.52, where it intersects the E gamma X curve. And then the E gamma X becomes the lowest energy all the way to x goes to 1. Remember, E gamma X is top of valence band measured from the bottom of the conduction band of X value. And now this is the lowest, which is the minimum. The X value becomes the minimum of conduction band. So this part is indirect band gap. So aluminum nitride is the indirect band gap. Gallium nitride is a direct band gap. The crossover from direct to indirect is at 0.52. So we should be looking, okay, at this rate curve, okay, from direct to indirect band gap. So from the graph, deduce if gallium nitride, aluminum nitride is a direct or indirect gap semiconductors. So we already said gallium nitride is a direct and aluminum nitride is indirect band gap. What is the X value for the crossover from direct to indirect? We have already seen is at 0, X goes 0.52. Is aluminum gallium nitride direct or indirect? What is the band gap? So aluminum is 0.7. Okay. So X equals to 0.7. So when x goes 0.7, you can read out from the graph. Or it will be on the E gamma x value. X goes 0.7. You want to be exact, you can substitute into this equation E gamma x for 0.7. You will get the band gap energy value, okay, for the aluminum gallium nitride with 0.7 or with 70% of aluminum. Okay. So x goes 0.7, we can read off, or you can substitute into the gamma x value of 0.7. You get 4.813 eV. So the intercept of two curves you can read from the graph, or you can equate these two equations to get x goes 0.52. Next, effective mass. Using linear interpolation method to calculate the effective mass of the valence band and the lowest conduction value of aluminum gallium nitride. Hence, calculate its reduced effective mass. Now, the lowest conduction value occur for 0.7. Okay, composition 0.7 is this curve, E gamma x. So we will ignore this and these two curves. Okay, the lowest conduction value. So when you use the effective mass, we'll look for the conduction band x value. Okay, for gallium nitride and aluminum nitride effective mass. So by linear interpolation, we just need to do the weighted average of x1 minus x. So the x is on the aluminum. Okay, 1 minus x on the gallium. So the aluminum nitride, gallium nitride. Effective mass of aluminum nitride and effective mass of gallium nitride is given to you. So that is 0.31 and 0.3. So we use the conduction band x value because the question asks for the lowest conduction band at x goes to 0.7, which is the at the x value respect to the top of the conduction band. Similarly for whole effective mass, again you do the weighted average. So the whole effective mass, okay, taken to be the average, okay, for gallium nitride and aluminum nitride for the whole, heavy whole and the light whole. You get the effective mass of the whole. So the reduced mass, okay, for aluminum gallium nitride, okay, you have to take this value and calculate the reduced mass. Okay, reduced mass. Next question. Aluminum gallium nitride has a type 1 heterostructure. The conduction band offset to the valence band offset ratio, okay, heterojunction is 7/3. Design aluminum nitride, aluminum gallium nitride, aluminum nitride quantum well. So basically, aluminum gallium nitride is a well. Aluminum nitride here is the barrier with the conduction barrier height of 1 eV. Now the conduction barrier height is also the same as the conduction band offset. Calculate the composition such that aluminum gallium nitride has a direct band gap. And calculate this band gap for the value that you have obtained. So, if you draw the diagram, aluminum nitride, aluminum gallium nitride band gap, and aluminum nitride band gap. So this is a type 1 heterostructure to form the quantum well. So this formed by type 1 heterostructure. We know aluminum nitride band gap is 5.1 eV. okay, at this point. So we want to calculate the aluminum gallium nitride band gap. At what composition? So the conduction barrier height, which is this is the conduction barrier height or the conduction band offset, because electron is trapped in the well. So this is the barrier height, or sometimes we call that the conduction band offset. It's given as 1 eV. Delta EC over delta EV is 7/3. So delta EC is 1 eV. You can calculate delta EV to be 0.43 eV. Now, the conduction band offset plus the valence band offset is basically the difference between these two band gap. So delta EC plus delta EV is delta EG. And you know delta EC, and you know delta EV, you should be able to calculate the difference in the band gap between the two material, which is 1.43 eV. So the difference in the band gap is 1.43, is basically band gap aluminum nitride minus the band gap of aluminum gallium nitride. So that gives you 5.1 minus 5.1 minus 1.43. That gives you the band gap of the aluminum gallium nitride, which is 3.67 eV. Now, this band gap itself, again, okay, as we mentioned in the question, you want it to be a direct band gap. Therefore, I would take this equation, okay, since this equation governs the direct band gap of aluminum gallium nitride. Okay, because the question asks for direct band gap. So this is the equation that's going to govern the direct band gap material. So it's equate, the band gap itself will be equate to the direct band gap equation, which is this equation. And you solve for the composition. Okay, you will have two values. Okay, one of the value will be rejected. Okay, and the value that is between 0 and 1 will be accepted. So the X we obtain is 0.12. So what is the band gap of this composition of 0.12 for aluminum gallium nitride? Again, you plug into the direct band gap equation for 0.12, you get 3.681 eV. So this aluminum gallium nitride band gap is 3.681 eV. So 0.1, 0.12 will be somewhere around here. So 0.681 eV. So that's how you design the quantum well with type 1 heterostructure with a band gap of 3.61 eV, which is a direct band gap for the aluminum gallium nitride. Okay, this is a table show the band gap energy and band offset of some semiconductors. So the material system, silicon slash germanium, silicon slash gallium phosphide. So this is A material, this is B material. So the band gap of silicon is 1.12. The band gap of germanium is 0.67. So for example, I take indium phosphide, cadmium sulfide. Material A is indium phosphide, cadmium sulfide is material B. The band gap of indium phosphide is 1.34. Band gap of cadmium sulfide is 2.42. Now, the conduction band offset, the valence band offset is given to you, and the ratio of the the valence band offset over the change in the band gap is also given to you. Now, the valence band offset, there are positive value, there are negative value. So basically, in this table, it was defined, okay, A/B material system. So delta EV, the valence band offset, is positive if the top of valence band of semiconductor A is higher than that of semiconductor B. Okay, what does this mean? We shall show an illustration of the growth of indium phosphide and cadmium sulfide heterostructure. In all this material system, it does not tell you whether it's a type 1 or type 2A kind of a band alignment. So let us draw the band diagram for indium phosphide, cadmium sulfide heterostructure. So consider a cadmium sulfide indium phosphide heterostructure. Cadmium sulfide indium phosphide have a band gap of 2.42 and 1.34. The valence band offset between cadmium sulfide and indium phosphide is 1.63. And the indium phosphide valence band is higher than that of cadmium sulfide. So down here, you can see its positive value. Indium phosphide is A material, cadmium sulfide is B material, AB. And then you say that the top of valence band of semiconductor A, which is indium phosphide, is higher than that of semiconductor B. Okay, so indium phosphide valence band is higher than that of cadmium sulfide. So let us find the conduction band offset of cadmium sulfide indium phosphide heterostructure and whether it form a type 1 or type 2 band alignment. So you basically need to sketch the diagram to show the band alignment, okay, of this heterostructure. So indium phosphide valence band is higher than that of cadmium sulfide, okay, for this question. So you draw the valence band, let's say 2 line, indium phosphide valence band higher than that of the cadmium sulfide. So that gives you delta EV to be 1.63 EV, delta EV, which is the valence band offset given to you. Next, I draw the indium phosphide band gap, which is 1.34 EV. Okay, so from top of valence band, I draw upwards. That give me the band gap of indium phosphide, 1.34 EV. Next, I draw the cadmium sulfide. I draw it upwards, and that gave me 2.42 EV. So I draw 2.42. Okay. So 2.42. Okay, imagine if I draw 2.42, basically from here, it's only 1.63. So I add a bit more of 0.79. Okay, so this is 2.42. Okay, it will not overshot this line. So 2.42 is basically 1.63 plus 0.79. So that give me the band gap of cadmium sulfide. So the remaining must be the conduction band offset of 0.55 EB. So the conduction band offset is 0.55 EB. So this is a type, straight away you can see there is a type 2A band alignment. It's staggered. Okay, a step. So it's staggered. So delta EC, okay, this delta EC is basically the band gap of indium phosphide plus the valence band offset. So this value plus this value minus the cadmium sulfide band gap. That will give you the conduction band offset. So that is the equation. And you can easily find, okay, instead of from the schematic diagram that you have drawn, you can calculate the value, or you can calculate from here. indium phosphide 1.34, valence band offset is 1.63, cadmium sulfide is 2.42, that gives you 0.55 EV. The difference in band gap, okay, the difference in the band gap, delta EG, is basically delta EV minus delta EC, okay, based on this equation. Okay, you can rearrange this term to get band gap of cadmium sulfide minus the band gap of indium phosphide. Okay, just bring over the term, you will get delta EV minus delta EC, which is the change in the band gap. Okay, energy for type 2 band alignment. In type 1, remember delta EG is basically delta EC plus delta EV. So this is a type 2 band alignment. And you can check from table 3.2.1. Okay, delta EV over delta EG is 1.51. Delta EV over delta EG from the table is 1.51. Delta EV is 1.63. Delta EG, okay, can be found if you know delta EV, because the whole equation goes 1.51. So delta EG is 1.08 EV. So you can just simply take the band gap, 2.42 minus 1.34. That gives you 1.08 EV. And you can simply make a guess, because for type 1 heterostructure, you know the change in band gap 1.08 will be just delta EC plus delta EV. And delta EV is 1.63. Then you try to find the delta EC. But however, in this case, this is a type 2 band alignment. So it's no longer delta EC plus delta EV, but it's delta EV minus delta EC. Okay, you can do that by intuition. We'll stop here. In the next session, we'll discuss the overview of low dimensional structure.